Welcome, Curious Minds, to the Deep Dive. If you've ever wanted a shortcut to really understanding our cosmic home, the Milky Way, well, this is probably it. Today, we're diving deep into the European Space Agency's Gaia spacecraft.
Yeah.
It's been this incredibly diligent cosmic cartographer for over a decade, and it has just wrapped up its mission, an extraordinary journey.
That's absolutely right. Gaia's primary goal was, well, it was nothing short of revolutionary, really, to measure the positions, distances, and motions of stars with just breathtaking precision. The ambition to construct the largest, most precise 3D map of our galaxy ever made. We're talking approximately 1 billion astronomical objects, a truly staggering number. And that includes not just stars, but planets, comets, asteroids, even distant quasars.
Wow. And for you listening, this deep dive is really designed to give you those surprising facts, those aha moments about the Milky Way.
Yeah.
You get a profound, sort of tangible understanding of our place in the universe, but without, feeling totally overwhelmed. All the insights we're sharing come straight from the detailed scientific overview of the Gaia mission itself. So let's get started.
Okay, so to really get our heads around Gaia's ambition, what exactly is it? And, why such a huge undertaking?
Right. So at its core, Gaia is an optical space observatory from ESA, the European Space Agency. It launched back in 2013 and just finished up operations in March 2025.
And it followed another mission, didn't it?
Yes, exactly. It's the direct successor to Hipparcos, which ran in the late 80s, early 90s.
Yeah.
Gaia basically took what Hipparcos did and multiplied its precision by like 100 times.
Yeah.
A massive leap. It was a key part of ESA's long-term science program, Horizon 2000 plus GandM.
Oh, and I heard its name has a bit of a story. Huh, yeah, a little bit. Originally, it stood for Global Astrometric Interferometer for Astrophysics. But the technique, the optical technique, actually changed during development.
Oh, really?
Yeah, but they kept the name Gaia anyway. Guess it's stuck.
Okay. And this wasn't cheap, I imagine.
Definitely not. We're talking around 740 million euros, about $1 billion US. And yeah, it finished a couple of years late and about 16% over budget.
Why was that?
Mostly down to some really tricky technical challenges. Polishing its special silicon carbide mirrors was apparently very difficult. And assembling the focal plane camera system, that massive detector, was also super complex.
Right, okay. So a complex beast.
Indeed. But the sheer scale of the science really justified that investment, Gaia had these core objectives that fundamentally changed things. First, measuring parallax with extreme precision.
Parallax. That's the tiny shift we see in a star's position as Gaia orbits the sun.
Right.
Tells us the distance.
Exactly. And nailing that distance lets us figure out a star's true intrinsic brightness, its luminosity. Knowing that is crucial. It helps us calibrate what we call standard candles.
Like those Cepheid variable stars.
Precisely. Stars with a known brightness. If we know how bright they really are and how bright they look, we can calculate distances much further out. That helps refine distance scales across the universe, even improves our measure of how fast the universe is expanding.
Wow. Okay, so big picture stuff from tiny measurements.
Definitely. Second, by observing 1 billion objects, about 1% of all the stars in the Milky Way, Gaia gave us this unprecedented, unbiased view of stellar populations, what kinds of stars are out there, how common are different types, all that. And this huge data set, observing so many stars over such a long time, gave amazing insights into rapid phases of stellar evolution, too.
And the third thing.
The dynamics. By mapping not just where stars are, but how they're moving their positions and motions across the sky, Gaia provided the critical data to understand how our whole galaxy works, how it formed, how it spins, how different groups of stars interact. And just to reiterate the scale, about 1 billion objects monitored, including thousands of Jupiter-sized exoplanets, 500,000 quasars, tens of thousands of asteroids and comets, and each one observed roughly 70 times over the main mission.
That is just a staggering amount of data. Okay, so how on Earth, how 1.5 million kilometers from Earth did Gaia achieve that accuracy? The launch itself sounds like a big deal. December 19, 2013, Soyuz rocket, French Guiana.
Yep, and then it traveled to its operational spot.
AL2 point.
Exactly, a Lissajous orbit around the Sun-Earth L2 Lagrangian point.
Why there? What's special about L2?
Think of it like a gravitational balancing point out beyond Earth's orbit. It's incredibly stable, both gravitationally and thermally. Very cold, very constant temperature. And crucially, the Earth and Sun are always in roughly the same direction, so Gaia could point its telescopes away without sun blockage, giving it a clear view.
Makes sense. And the spacecraft design itself sounds pretty innovative, that huge sun shield.
Oh yeah, 10 meters across. And it wasn't just shade, it stayed at a fixed 45-degree angle to the sun, and the whole spacecraft sort of precessed, slowly spun to scan the sky. This kept the telescopes incredibly cold, which is vital for infrared and precise optical measurements. We're talking minus 170 Celsius.
Brr.
But the sun-facing side, with the solar panels, could get up to 70 degrees C, so huge temperature extremes. And it also generated all the power for the spacecraft.
And the way it pointed itself was unique too, right? No reaction wheels.
That's right, no traditional spinning wheels or gyroscopes for pointing. Instead, it used these tiny thrusters firing incredibly small puffs of cold nitrogen gas, like
All right.
1.5 micrograms per second.
Micrograms.
Yeah, minuscule amounts. But it provided super fine, super stable pointing control, mounted on this incredibly rigid silicon carbide frame, essential for the measurements.
Okay, so that stability was key for the instruments. What were they actually measuring?
Right, the payload. 3 main scientific instruments. First, the astrometry instrument, or ASTRO, that was Gaia's core. Its job was to pin down the angular positions, the parallax for distance, and the proper motion for stars greater than magnitude 20.
Proper motion. That's the star's movement across the sky as we see it.
Exactly, its velocity projected onto the plane of the sky. Then you had the photometric instrument, BPRP, for blue and red photometers. This measured the brightness and color of stars across a wide spectrum. Analyzing that light tells you about the star's properties, its temperature, mass, age, even what elements it's made of. Again, down to magnitude 20.
Okay. And the third one?
The radial velocity spectrometer, RVS. This measured velocity along our line of sight. Is the star moving towards us or away from us? It did this by taking high-resolution spectra, basically splitting the star's light into a rainbow, and looking for Doppler shifts. This worked for stars up to magnitude 17, and these radial velocity measurements are absolutely vital. They help correct for something called perspective acceleration.
Perspective acceleration.
Yeah, it's the apparent acceleration stars seem to have just because we, the solar system, are moving around the galactic center. RVS helps untangle that.
Got it. So how did it all work together to get that precision, the scanning?
It was ingenious. Gaia had 2 telescopes looking out at a fixed angle of 106.5 degrees from each other. The whole spacecraft rotated continuously, once every 6 hours. This swept the 2 fields of view across the sky in a great circle, scanning a strip about 0.7 degrees wide.
Okay.
And then the spin axis itself slowly precessed, tracing out a cone shape over 63 days. This combination meant it scanned the entire sky multiple times in a complex, overlapping pattern over the mission lifetime.
And the camera system, you mentioned it was huge.
Oh, immense. The focal plane array was about 1 meter by half a meter, packed with 106 very sensitive CCD detectors, altogether nearly a gigapixel, 1 billion pixels staring at the sky.
Incredible.
Each star or object would rift across this focal plane and get measured by multiple CCDs as the spacecraft rotated. And an onboard atomic clock, a rubidium one, ensured the timing of each observation was known to nanosecond precision. Absolutely critical.
And all this feeds into, what was it, the BCRS?
Yes, the barycentric celestial reference system. Think of it as the ultimate cosmic coordinate grid. It's the fundamental reference frame used in astronomy and navigation, defined by the positions of distant quasars. Gaia's data massively improved the BCRS, making it incredibly precise. It even has to account for things like Einstein's relativity, like light bending around massive objects.
Yeah, what kind of accuracy are we talking about in the end?
It's truly mind-boggling. For brighter stars, say magnitudes 3 to 12, the accuracy for position and parallax reached about 6.7 microarc seconds or even better.
Microarc seconds. How small is that?
It's tiny, like seeing a coin on the moon from Earth. Or, as the saying goes, identifying someone's left eye if they were standing on the moon.
Ew.
For fainter stars, near magnitude 20, it was still hundreds of microarc seconds.
Okay.
Compare that to Hipparcos, its predecessor.
Yeah.
Its very best accuracy was around 100 microarc seconds. Gaia was a whole different league.
That's just, yeah. Mind-boggling is the word. But, missions this complex rarely go perfectly smoothly. Gaia must have faced some challenges.
Oh, absolutely. No mission escapes unexpected hurdles. Right from the start, actually. The launch itself got pushed back a bit in October 2013.
Why was that?
Well, it was purely precautionary. They decided to replace 2 transponders on the rocket. Apparently, an identical component had failed on a completely different satellite, so they took no chances. Better safe than sorry.
Sensible. What else?
Then, not long after launch, the team noticed something unexpected. Stray light was getting into the telescopes. More than anticipated.
Stray light. Where from?
Initially, they thought it might be ice forming on the spacecraft and scattering sunlight. But it turned out to be, well, it was microscopic fibers from the edge of the sunshield itself kind of poking out and catching the light.
Ah, did that cause big problems?
It had an impact, yeah, but thankfully modest overall. It mainly affected the measurements of the faintest stars, and it hit the RVS spectrograph a bit harder. But the engineers were brilliant. They developed mitigation strategies, software fixes basically to minimize the effect. It's funny, there was actually a similar issue with stray light baffling on an infrared telescope flown on the space shuttle decades ago. History repeating itself, sort of.
Always something. And I heard there were issues later on, too, like getting hit by something.
You're right. Much later, in April 2024, Gaia actually got hit by a tiny micrometeoroid. Space dust, essentially. It damaged part of its protective cover, which caused some occasional disruptions from stray sunlight getting in.
Ouch.
And then, just in May 2024, one of the CCD detectors failed. It started producing false detections, so the engineers had to perform one final, very delicate refocusing of Gaia's optics to work around it.
Wow. Despite all that, it sounds like it was incredibly resilient. Did these issues ever really threaten the main science goals?
You know, the team was always confident they could handle it. The impact on the core mission, the really bright stars, and the overall map was pretty minimal. It really speaks volumes about the spacecraft's robust design and the quick thinking of the operations team back on Earth. They kept finding solutions.
Which probably explains why the mission kept getting extended.
Exactly. It was initially planned for 5 years, but it got extended multiple times, first to 2020, then 2022, and finally that indicative extension to early 2025.
Why? Did it just keep working better than expected?
Pretty much. The detectors, those CCDs, were degrading much, much slower than the engineers had predicted. They were incredibly durable.
So what finally limited its lifespan?
It came down to fuel, essentially.
Oh.
The nitrogen gas for those tiny micropropulsion thrusters, that cold gas was absolutely essential for the super precise pointing needed for the measurements. Eventually, you just run out.
Right, like a car running out of gas.
Sort of, yeah. A very, very precise car. Oh, another interesting thing. Gaia actually performed better than planned in one respect. It was designed to observe stars fainter than magnitude 5.7. Brighter stars were thought to saturate the detectors. But during commissioning, they realized it could actually handle stars as bright as magnitude 3. So they expanded its routine observing range to cover magnitude 3 all the way down to 20. A great bonus, captured many more famous bright stars.
That's fantastic. So after all those years, all those observations, overcoming the challenges, what did it all give us? Let's get into the data and the discoveries. The sheer volume sounds immense.
Oh, it is. Around 60 terabytes of raw data downloaded from the spacecraft itself. Once processed and uncompressed on the ground, that swells to about 200 terabytes of usable science data. Just enormous.
200 terabytes? How is all that even processed?
It takes a huge effort by a dedicated consortium across Europe. It's called DPAC, the Data Processing and Analysis Consortium. Hundreds of scientists and engineers, funded by the participating ESA member states, working for years to turn those raw signals into meaningful catalogs.
And getting the data down from L2, how did that work?
Gaia transmitted data back to Earth for about 8 hours every day at a rate of 5 megabits per second, which is, decent, but not super fast by today's standards. The signals were picked up by ESA's big ESTRAC network dishes, antennas in Spain, Argentina, Australia, tracking Gaia as the Earth rotated.
Okay. And this data came out in stages, right? These data releases.
Exactly. The data releases themselves kind of tell the story of the mission's progress, each one building on the last with more data and better processing. DR1, Data Release 1, came out in September 2016. That was the first big map. It gave positions and brightness for 1.1 billion stars, a huge number right off the bat. It also combined early Gaia data with the older Hipparcos data to get positions, parallax, and proper motions for about 2 million brighter stars, a first taste of the 3D motion map. Plus light curves for some variable stars and positions for over 2,000 quasars to start anchoring that reference frame, the BCRS.
So that laid the groundwork.
Precisely. Then came DR2 in April 2018, based on 22 months of observations. This was a really big leap. It gave us positions, parallax, and proper motions, the full 3D position in 2D motion for a massive 1.3 billion stars, plus color information, the photometry, for 1.1 billion stars, and crucially, the first radial velocities, that line of sight motion, for 7 million stars. Suddenly, the galaxy wasn't just a static picture. We could see its movement in 3 dimensions. It also included data on 14,000 asteroids and comets.
Game changer, sounds like.
Absolutely. Then came EDR3, the early data release 3, in December 2020, based on 34 months of data. This focused on even better astrometry positions, parallax, proper motions with improved precision. It also delivered a new, even more accurate celestial reference frame, Gaia CRF3, based on 1.6 million quasars and galaxies. And it gave us the Gaia catalog of nearby stars, over 330,000 stars within about 330 light years. Our local neighborhood mapped like never before.
Wow, our backyard in detail.
Exactly. And the full DR3 followed in June 2022. This included everything from EDR3, but added a whole lot more. Much more solar system data, loads on variable stars, information on binary and multiple star systems, more quasars, even data on extended objects like galaxies and nebulae, and critically, astrophysical parameters derive properties like temperature, gravity, metallicity for hundreds of millions of stars. That's where you really start doing astrophysics.
Okay, so each release added more layers, more detail. What's next?
We're now looking forward to DR4, Data Release 4. It's planned for no earlier than mid-2026. That's expected to use even more data and improved processing, aiming for astrometric precision about 1.7 times better than DR2.
Another big jump.
Hopefully. And then the final catalog, the ultimate product, DR5. That's tentatively scheduled for no earlier than the end of 2030. That should incorporate all the mission data, processed with the final calibrations and algorithms. It's aiming to be about 1.4 times more precise again than DR4. And the best part, all this data, every release, is made completely public, free to access online for anyone in the world.
That's fantastic for science. Okay, so with all this incredible data, what are some of the biggest discoveries, the real headline grabbers? Well, starting with mapping the galaxy's structure and history, Gaia has been truly revolutionary. Back in October 2018, remember the discovery of Gaia Enceladus?
Oh yeah, the sausage. That was huge.
Right. The remnants of this massive galaxy that merged with the Milky Way about 10 billion years ago. And the data suggested this merger essentially created a big part of our galaxy, the thick disk. It's linked to a bunch of globular clusters, too. It's like finding the foundation stones of the Milky Way.
A major piece of galactic archaeology.
Definitely. Then just a month later, November 2018, came Antlia 2, this enormous ghostly galaxy, as big as the Large Magellanic Cloud, but 10,000 times fainter.
Yeah, the lowest surface brightness galaxy ever found. Really challenges our ideas about dark matter and how galaxies form, doesn't it? Suggests there might be many more like it hiding out there.
Exactly. Fast forward to January 2020, and the Radcliffe Wave was announced. This enormous wave-like structure made of gas stretching thousands of light years, and it's a major nursery for new stars right in our galactic neighborhood.
It completely changed our view of local star formation. We thought these regions were more scattered, but this showed a huge, coherent structure linking many of them.
And even more recently, March 2024, Gaia helped uncover Shakti and Shiva. These two ancient streams of stars formed over 12 billion years ago, maybe even before the Gaia Enceladus merger.
Fossils from the Milky Way's very, very early days. Incredible find.
It really is rewriting the history books.
And beyond the big structures, Gaia's been amazing for understanding stellar systems and populations too. Like the Gaia ESO survey back in 2017. Using Gaia data, they pinned down lots of binary, triple, even quadruple star systems, including one, HD 74438, that looks like it might be a future Type Ia supernova. Those are crucial for measuring cosmic distances.
Right, the standard candles again.
Exactly. And then there was the Sculptor Dwarf Galaxy result, also in 2017. Gaia measured its 3D motion with such precision. They said it was like seeing something smaller than a pinhead move on the moon viewed from Earth.
That tiny motion revealed its orbit around the Milky Way is highly elliptical. Tells us how these small galaxies interact and merge with bigger ones.
And what about those hyper runaway stars found in 2018?
Oh yeah. Stars moving so fast they're literally being ejected from the Milky Way.
Some are leaving, some are actually coming in, maybe from other galaxies, though there were some data caveats there.
Still, it points to incredibly energetic events, right? Maybe interactions near the supermassive black hole at the galactic center, or powerful supernova kicks.
Extreme astrophysics in action.
And Gaia hasn't just looked outwards. It's told us things about our own solar system and its place in the cosmos. Like in November 2020, it measured the solar system's acceleration towards the galactic center. Tiny, tiny number, 0.23 nanometers per second squared.
Seems small, but knowing that precise motion is vital for correcting all other astronomical measurements.
Absolutely. And then there's the whole exoplanet revolution Gaia is contributing to. It found its first transiting exoplanet, Gaia 1b, a Jupiter-sized world, confirmed in 2022, along with Gaia 2b.
Right, finding planets by the dip in starlight as they pass in front.
But then, in September 2023, came Gaia 3b. And this was special, wasn't it?
Yes. Gaia 3b, another giant planet, was the first exoplanet confirmed solely through astrometry. Gaia detected the tiny wobble the planet's gravity induces on its host star as they orbit their common center of mass.
Proving Gaia's core technique could find planets directly. That's huge.
A major milestone. And it also found one via microlensing, Gaia 22D carry Phi, so it's using multiple techniques.
And it's even finding black holes. Gaia BH1, discovered in November 2022, the closest known black hole to Earth, about 1,600 light years away.
Right, a stellar mass black hole with a sun-like star orbiting it, found because Gaia saw the stars wobble, but there was no visible companion causing it.
Just empty space where something massive had to be. Amazing. And then Gaia BH2 followed in February 2023.
These discoveries are helping us find the population of dormant black holes, which are really hard to spot otherwise.
And looking ahead, there's a plan to use Gaia data to build a detailed 3D map of interstellar dust in the Milky Way.
Yes, expected around 2025, that will be invaluable for understanding how starlight gets dimmed and reddened as it travels through the galaxy, crucial for interpreting observations.
Wow. The discoveries just keep coming. But the spacecraft's operational journey itself, that part is now over. Its final targeted observation was January 10th, 2025.
That's right. End of an era for the flight team.
And then it was officially decommissioned on March 27th, 2025. What does that involve?
Well, before switching everything off, they commanded Gaia to perform a final engine burn. Not a big one, just enough to nudge it out of its L2 orbit and into a stable heliocentric path, orbiting the sun independently.
Why do that?
To make sure it doesn't interfere with any future missions that might want to use the L2 region. Good orbital hygiene, basically. And of course, they made sure all the remaining science and engineering data stored on board was successfully downlinked first.
So the spacecraft is silent now, drifting around the sun, but the mission isn't truly over.
Not at all. It's now entered the crucial post-operations phase. All the focus for the DPAC consortium for the next several years is on refining the data processing, understanding all the instrument calibrations perfectly, and producing those final definitive data releases, especially DR5, which is slated for the end of 2030. That's the grand finale catalog.
So the analysis and discoveries will continue for years, decades even.
Absolutely. Gaia's legacy is still unfolding, and people are already thinking about what comes next. There's a proposal being studied called Gaia Gaia near infrared.
Expanding into infrared.
Exactly. The idea would be to build on Gaia's success, but observe in near-infrared light that would let it see through dust much better, map the obscured regions of the galaxy, study cooler stars, and potentially improve precision even further. It's one of the concepts being considered for ESA's big Voyage 2050 science program. So the spirit of Gaia might fly again.
That's exciting to think about.
Yeah, so summing it all up, Gaia really has been a monumental achievement in space science. It meticulously built the most precise, most comprehensive 3D map of our galaxy ever conceived. There's just nothing else like it. It's fundamentally transformed how we understand the Milky Way. Its birth, its structure, how it moves, how it's still evolving. It's like we were living in a house and suddenly someone handed us the complete architectural blueprints.
That's a great way to put it. And with this extraordinary new atlas of our galactic neighborhood, just think about that. How mapping something so vast, so ancient, can actually reveal the tiniest, most surprising details about the universe around us. And it's definitely going to shape where we look next. So here's a thought for you. What new cosmic questions will you explore now that we have this incredible map? If you want to dive in yourself seriously, look up Gaia Sky. It's this amazing free visualization tool where you can actually fly through Gaia's data in 3D. It's mind-blowing.